Hey, welcome back to Chemistry Online. Our topic today is chemical equilibrium. Chemical equilibrium. Now, there are so many areas of life where you experience equilibrium. Like, for instance, you are in a playground and you're using the seesaw. If the weight of one person on the other end of the seesaw is heavier than the other person at the other end, the seesaw goes down, bends to the heavier side. And so to counter that weight, you have to add more weight, increase, or the other side reduces its weight for it to attain equilibrium. Or take, for instance, you go to a gym, where you want to do your workouts, and you're using a treadmill. A treadmill, some people call it tread wheel, but it's that stuff where you put it on and it starts going backwards, and when you climb on it, you run forward while it's going backwards. That's the treadmill. You must be in constant motion if you're using a treadmill. Tell you why. Although you're neither moving forward nor backwards, because as fast as you're running forward, the treadmill is moving you backwards. So you're kind of in a constant motion actually, but you're in the same position because the treadmill is moving backward, you're moving forward, and that's kind of stalls the real motion. You will fall down if you try to slow down your pace. So if you're getting tired, you either reduce the speed of the treadmill or you increase your own speed so that yourself and the treadmill run at the same rate. That way you're in equilibrium with the treadmill. Apart from that, nature always tends to attain equilibrium. Take for instance, if you remove a bottle of cold drink from a fridge and drop it on a table, I tell you what, until the temperature of the cold drink becomes same as the temperature of the surrounding air, nature won't stop. So that's a way of attaining equilibrium. Till the temperature of the cold drink becomes the same as the temperature of the surrounding air, that they are in equilibrium. The same happens for a hot body. If you bring a hot iron out of fire and drop it outside, and you see it starts cooling because the surrounding air wants to bring it to the same temperature with itself. So until it gets to that temperature where the hot iron is now the same temperature with the air, and as you call it, is cool. It's cold now, and that's equilibrium. Until that happens, nature keeps working. So I don't know any area of your life or any area of day-to-day life where you don't need equilibrium. Oh, okay, except in your spiritual life, where if your righteousness does not exceed that of the scribes and the Pharisees, you cannot enter the kingdom of heaven. Oh, well, except you're trying to be like Christ, because the Bible wants you to be like Jesus, okay? All right, that's the equilibrium you should try to attain as a Christian. Worst of it all is if as a Christian you're trying to compare or attain equilibrium with a sinner. It's called unequal yoking. So that's not the equilibrium we want. So apart from that, equilibrium is what nature always tries to attain. Now we're going to see how we can use the knowledge of this natural equilibrium and equilibrium in chemicals. Chemicals react, and then at the point you have a mixture that is homogeneous. Take for instance titration. We say if you're titrating an acid against a base, if you use a good indicator, say methyl orange, phenolphthalein, if you use an indicator That indicator helps you to know when that reaction attains equilibrium. It's when you see the color change. So we're coming now to chemicals. So chemical equilibrium. Dynamic equilibrium is a state of a system where there is no observable change in the properties of the system with respect to time. So with that, we can define chemical equilibrium as a state in which the rate of the forward reaction equals the rate of the backward reaction. In other words, there is no net change in concentrations of the reactants and products. They're equal. So you see the rate of consumption of the reactants is the same as the rate of production of the products. So no change, no net change. That is equilibrium. That means that the reactants undergo a change in composition to form the products, which in turn are reconverted to the original reactants at the same rates. So a chemical equilibrium can only be achieved in a closed system. You have two types of systems, open system and a closed system. You can use a simple illustration where you have a cup of water, actually 2 cups of water, and 1 cup of water, one of the glass of water is open while the other one is closed. Just use something to cover the top of the other cup of water, and so you keep both of them, maybe under sunlight. With time, you discover that the one that is open gets reduced. Why? Because of evaporation. So the heat from the surrounding tries to evaporate the water from the cup. So the level of the water from the open cup reduces with time. One day it will get finished. But there is no change to the other cup of water that was closed. That's because when heat tries to evaporate the water molecules, it actually evaporates it, but when it goes up to leave the cup, it meets a closure, meets a top. So it bounces there and recondenses. When it leaves the water body, it becomes vapor. So it goes out there and hits a surface. It stays there and recondenses, comes back as liquid into the cup. So you call that equilibrium, because the same amount of water going up recondenses at the top of the cup and comes back to the water body, and so the water body does not change with time. So that's equilibrium. So equilibrium can only be achieved in a closed system. If you use an open system, the reactants keep being consumed, and no product is, the products are not reconverted back to the reactant, because the environment is so wide open and your reactant just gets consumed. And so in a closed system, no substance can enter or leave the system. So that's where it's possible to achieve equilibrium. All right. Take note that in a closed system, a change in Gibbs energy is 0. That's change in free energy is 0. Okay. So now also, in reactions, the reactants are converted to products, and we say that some of them can be converted back to the reactants. Yes, the product can be converted back into reactants. Others don't. So these reactions where the reactants are consumed to form a product, but the product can be reconverted back to the reactants, are called reversible reactions. That means these reactions can go either way, can go forward and backward. So these reversible reactions can attain equilibrium, because it can go forward and come back. So at the point, the rate at which it goes forward is the same as that it's coming back. That's backward action. So can attain equilibrium there. And if reversible reactions are always identified by a double arrow, one of the arrows facing the right hand side, the other one facing the left hand side. So when you see that sign, it means that reaction is reversible, that it can go either way. And this sign is written between the reactant and the product, so it's at the center. Reactant on the left hand side, product on the right hand side, and the double arrow showing a reversible reaction at the center, separating both of them. Now, a reversible reaction is one that proceeds in both directions under suitable conditions. Under suitable conditions. Now, when both the forward and the backward reactions of a reversible reaction are occurring at the same rates, at the same speed, then you say that that reversible reaction is in dynamic equilibrium. So you see it produces no net change in the concentrations of the reactants or products, because it's the same rate of reactants, the same amount of concentration of reactant that's converted to products, so it's reconverted back. No net change. Nothing changes. Alright. Now, so let's look at equilibrium constants, denoted by the letter K. Equilibrium constants. Now, listen to this law. The law of mass action, it was propounded by Goldberg and Wage. So the law of mass action states that at constant temperature, the rate of reaction is proportional to the active masses of each of the reactants. The rate of reaction, the speed of reaction, speed of formation of products, and the reconversion of the reactants as the rate of reaction is proportional to the active masses, the masses that are actually reacting, the active masses of each of the reactants. The reactants are combined to form the product. So that's the law of mass action. Now, the active mass of a substance is the concentration of that substance raised to the power of its coefficients. You know what coefficient is? The big number standing in a reaction, as you can call the mole number. In most cases, the active masses of the reactants may be taken as their molecular concentrations. So we'll see how to do that when we are doing calculations in chemical equilibrium. But let's look at Le Chatelier's principle. Le Chatelier's principle. Now, every reversible reaction reaches its own specific equilibrium under a given set of conditions. Now, these conditions depend on, number one, the temperature of the reacting system. Number two, the pressure of the reacting system. That's for gases. Gases deal with pressure. And then number three, the concentration of the reacting system. So take note of these three conditions, the three variables. A change in any one of these three factors will upset the balance of the system, and so it will result in a shift in the position of the equilibrium. Take notes. Listen very well to Le Chatelier's principle. Le Chatelier's principle states that if an external constraint, such as a change in temperature, a change in pressure, or a change in concentration, if such external constraints is imposed on a chemical system in equilibrium, then the equilibrium will shift so as to annul. The equilibrium will shift so as to neutralize that constraint. That is, if you change the temperature of a system that's already in equilibrium, the equilibrium position of that system will shift so that it can accommodate this change and try to bring back the system to equilibrium. Try to get that. Now we'll see how these different constraints, different stresses on an equilibrium system, how they affect the equilibrium system, one by one. Because we mentioned temperature, change in temperature, change in pressure, change in concentration. Let's look at them one by one. How does temperature affect the equilibrium constants? How does pressure, how does concentration, how do they affect them? So let's look at temperature first. Effect of a change in temperature. Now, remember that for an endothermic reaction, heat is absorbed in the reaction. And when that happens, the value of change in heat is positive. So remember, endothermic reaction has positive change in heat value. That means for an endothermic reaction, we can picture heat as being a reactant. Because, heat is absorbed into the system. So heat is one of the reactants now. Good. Now, but for an exothermic reaction, the situation is just the opposite. Heat is released, you know that. So heat is a product. So, since it's losing heat, that means change in heat is negative. Remember that. If we picture heat as a reactant or a product, we can apply Le Chatelier's principle. That is, if we raise the temperature of an endothermic reaction, it is like adding more reactant to the system. Remember, heat is added, is absorbed. So if you raise the temperature of an endothermic reaction, that means you are adding more heat to that reaction. So adding more heat is like adding more reactants to that system. And therefore, by Le Chatelier's principle, the equilibrium will shift to the right, that's the product side, as the value of equilibrium constant increases. So you see how the equilibrium shifts to kind of neutralize that constraint. What's the constraint? Addition of temperature, addition of heat. So that constraint, that stress was introduced into a system that was already in equilibrium. So the equilibrium will shift to the product side because now you are adding more reactants. It will shift to the equilibrium to the product side to try to neutralize that constraint. Now, conversely, if you lower the temperature of an endothermic reaction, the equilibrium will shift to the left, as to the reactants, because lowering the temperature in this case is just like removing a reactant. So when you added the reactants, you are giving the product more space. What will be formed will now be more. So that shifted the equilibrium position to the right. But since you are taking out heat now, as you are removing some reactants, the equilibrium position shifts back to the left to try and accommodate the change, annul it, neutralize it, and equilibrium is restored. Okay. Now, for an exothermic reaction, the heat is not a reactant, because exothermic reactions will be releasing energy, releasing heat. So heat is a product. Therefore, increasing the temperature will cause a decrease in the equilibrium constants, which as a result will shift the equilibrium to the left. You know that. While if you are decreasing the temperature, it will shift the equilibrium to the right. Understand that. Just compare it with when we were doing endothermic reactions, and then you will understand better. So take note that under this change in temperature, we are saying that a change in temperature will increase the equilibrium constants. The K value, the equilibrium constant is denoted by letter K. So change in temperature in an endothermic reaction will increase the equilibrium constants, while in an exothermic reaction will decrease the equilibrium constant. Take note, because only change in temperature can affect the equilibrium constant. Okay. Now let's look at an example there. There is a question there. In which direction will the equilibrium shift if the temperature is raised in the following reaction? Now listen to the reaction. N2O4, it's a gas, is in a reversible reaction, produces 2NO2, and the change in heat, the enthalpy change, is given as plus 57.2. That means it's positive. How do we solve this? Now, the question is asking you, in which direction will the equilibrium shift? And this is how you tackle this kind of question. And from the question, our heat of reaction is positive. Yes, plus 57.2. So since it's positive, it means the reaction is endothermic. Remember, endothermic reaction has positive change in heat. Now, if it's endothermic, then heat is a reactant. You remember, heat is added because it's endothermic. It's gaining more heat. So heat is added to the system. That means heat is a reactant. Is reacting also. Now, increasing the temperature will shift the equilibrium to the right, as we just explained before now. That is, equilibrium constants will increase. Remember, so shifting equilibrium position to the right increases the equilibrium constant. So shifting to the right means it's shifting to the product side. That means it will be producing more. In this case, producing more NO2. You understand me? Now, if you go to your textbook, page 270, you will see a table there, just at the bottom, page 270. Where you see a table of effects of changes in temperature on equilibrium of some reversible reactions. That question we just solved is there. I mean, the reaction is there. So you can go through them, those reactions in that table, and see how change in temperature affects the equilibrium constants and the position of equilibrium. Okay. Now let's see how pressure affects equilibrium. Effects of a change in pressure. Now, for a change in pressure to affect a system in equilibrium, number one of the reactants or one of the products in the reversible reaction must be a gas, must be gaseous. Number two, the total number of moles of gaseous molecules on the left side of the equation, as the reactants, must be different from the total number of moles of gaseous molecules on the right hand side. That's the product side. Take note of these two factors that affect change in pressure in equilibrium. A change in pressure or change in volume will result in an attempt to restore equilibrium by creating more or less moles of gas. Know why I said change in volume? If you remember your gas laws, volume is proportional to pressure. Pressure is proportional to volume. You increase the volume, pressure will increase. Decrease the volume, pressure will decrease. So a change in pressure or a change in volume will result in an attempt to restore equilibrium by creating more, depending on if it was increase in pressure or increase in volume, or less moles, if it was decrease in pressure or decrease in volume of the gas. If the pressure is increasing or the volume is decreasing, the equilibrium will shift to favor the side of the reaction that involves fewer moles of gas. That is prior to what I said, increase in pressure decreases volume. So if the pressure increases, volume will decrease. So if you decrease the volume, you are increasing pressure. And if you are increasing pressure, you are decreasing volume. So if the pressure increases, the volume will decrease. But then the equilibrium will shift to favor that side of the reaction that now has fewer moles of gases. Remember when we said that the moles of gases of the left-hand side should be different from that of the right-hand side. Now, similarly, if the pressure decreases, that the volume increases, if the pressure decreases, the production of additional moles of gas will be favored. That means more gases, more molecules of the products will be formed. So the equilibrium shifts to the product side and favors the products. Example, in the formation of ammonia from nitrogen and hydrogen, that's N2 plus 3H2 forms in a reversible reaction 2 moles of ammonia. And the change in heat, the enthalpy change is minus 92 kilojoule per mole. Now, in that formation of ammonia, 4 moles, that's volume, the volume of the reactants. 4 moles of reactants, that is 3 moles of hydrogen gas plus 1 mole of nitrogen gas, makes up 4 moles of the total reactants. 4 moles of the reactants give only 2 moles, that's 2 volumes, of the products. Remember, the total number of moles of the gaseous molecules on the reactant side must be different from that of the product side, because the equilibrium will have to shift to favor the side that has less moles. So if they are equal, the equilibrium is constant, so you have dynamic equilibrium. So we don't want that now. So here in the formation of ammonia, the reactants have 4 moles, and the products have 2 moles. So 4 moles reacted to give only 2 moles of the products, that's of ammonia. Now, increasing the pressure, if you're increasing the pressure by reducing the volume, you will favor the forward direction. Why? Because the forward direction, the product direction, has less or fewer moles of the gas. You remember? So, because we said that the equilibrium will shift to favor the side that have fewer moles. So, if you increase the pressure, the equilibrium will shift to the right to favor the forward direction, the product, by causing the equilibrium position to shift to the right. Therefore, increasing the yield of ammonia, that is, the production of ammonia will increase. So if you are in other ways asked, what should be done to increase the yield of ammonia in this reaction? Simply increasing the pressure, because the moles of products formed is fewer than that of the reactant. So if you increase the pressure, you yield more of the products. Now, on the other hand, lowering pressure, reducing the pressure, will cause the equilibrium position to shift to the left. There's no hard rule about that. You just know that. That means to favor the backward reaction. That's the reactants now. And what will it cause to the product side? It will reduce the yield. So it will increase, let's not go to reduce now. It will increase the yield of the reactants now, because it's favoring the reactants. It favors the backward direction. So it's favoring the reactants. That means it will increase the yield of the reactants. Understand that? Now, in the reaction, N2O4, like we saw in that former question we did on the change in temperature, that reaction, N2O4, in a reversible reaction to produce 2 moles of NO2, the number of moles of on the left hand side is lesser. You see that N2O4 is just N2O4, that's 1 mole. But in the product side, we have 2 moles of the product formed. So the number of moles of the left hand side, the reactant side, is lesser than that on the right hand side. Therefore, if you increase the pressure, it will favor the side that has fewer moles of the gas. So you already know that it will favor the backward reaction, favor the left hand side, the reactants, because it has fewer moles. So it will favor the backward reaction, since the equilibrium shifts to favor the side with fewer moles of gas. But if you lower the pressure, the equilibrium will shift to favor the forward direction. So take note of all this. So in summary of the pressure stuff, increasing the pressure forwards or favors the side with less or fewer moles of the gas, while reducing the pressure will favor the side, with the more moles of gases. All right. Now, in reversible reactions where the number of moles of gas on both sides of the reaction are equal, take for instance, in the formation of ferrium oxide. Okay, let's see the equation. 3Fe plus 4H2O in a reversible reaction yields Fe3O4 plus 4H2. Now let's count the number of moles of the gaseous molecules in that reaction. If you look at the left hand side of that reaction, ion Fe, ferrium, is not gas, it's not a gas, so you ignore the 3, ignore that one. Go to H2O. H2O is in gaseous form, so it has 4 moles, so we have 4 moles of the gaseous reactants now. If you go to the right hand side, Fe3O is not gas, so you pass that, go to the gas. H2 is a gas, and it has 4 moles, so the number of moles on the right hand side is the same as that in the left hand side. So when you have that, the system will be unaffected, will not be affected by change in pressure. Because, if you increase pressure in a system that is in equilibrium, it should affect the side that has lower or fewer number of or moles of the gas. But here we have the same moles of gas on both sides. So increase in pressure or decrease in pressure will not affect that system. But however, the rate at which equilibrium is attained will be faster at higher pressure. So it will just increase the speed, but it will not shift the equilibrium. It will not favor any other. It will not yield more of the reactants or the products. It will just increase the speed, the rates of the rates at which equilibrium is attained. That's if you increase the pressure. So we have seen increase in pressure, we have seen increase in, we have seen effects of change in pressure, we have seen that of change in temperature. Now let's see effects of change in concentration. In an equilibrium system, there is a balance between the concentration of the reactants and the products. That's why you balance equations, so that the concentration in the reactant side must be the same as that in the product side. If more reactants are introduced into the system, the balance will be upset. So you have to rebalance that equation. You understand that? In order to annul these constraints, the equilibrium position will have to shift to the right. That's the product side, because you added more reactants. So the product is now wanting, it's lacking. So the equilibrium will shift to that side to try to annul that, to try to neutralize that constraint, that stress. So the equilibrium position will shift to the right, product side, favoring the forward direction. This results in an increase in the concentration of the products. If you balance your equation, you see that happens. Or if you remove the products continually from the system, removing the products will reduce the products. You understand that? So it makes the reactants more than the products, because you are reducing the products. So it's not in equilibrium anymore. So because the products are less, the reactants are more, the equilibrium position will have to move to the right to favor the products, because the product is now less. It's also less. So it has to favor that side to try and see if it can increase that to balance up with the reactant, since it's more. Now, that's because the reaction will always favor the side that is opposing the addition of the species. Always favor the side that is opposites the addition of the reactants. So if you're adding more reactant, the reaction will favor the other side that is opposite the side that is adding. So if you're taking away, you are removing to favor that side, because the other side is more. Understand that, please. So in summary, for this concentration stuff, you see that increase in the reactants, adding more reactants, will make the equilibrium position to shift to the right to favor the product, because the product is now less, and the concentration of the product is less, so it wants to annul that stress to try and bring it back to equilibrium. The same thing as removing the products. If you try to keep removing the products, you keep reducing the product side, and that makes the reactant side more. So reducing the products will also make the equilibrium shift to favor that product side, because it's few, it's less. The concentration of the product becomes less as you keep removing. So now let's see how a catalyst can affect equilibrium. A catalyst does not change the position of equilibrium. Take notes. But also it cannot be used to increase product formation, but can be used to speed up or reduce the rate of the reaction. You know what a catalyst does. So it only goes in to speed up the rate of reaction or to slow down the rate of reaction. That's when we say rate, we mean the time it takes for the system to attain equilibrium. That's the rate of reaction. So that's what a catalyst does. A positive catalyst will increase the rates of both the forward and the backward reactions. How does it do that? By lowering the activation energy of the reaction. But the other way round, a negative catalyst will slow down the rate of reaction so that a longer time is needed to reach equilibrium. Okay, so let's try and summarize this chemical equilibrium and these factors that affect chemical equilibrium. So in summary, only three stresses can affect the equilibrium position of a reversible reaction. As we have change in concentration, we have change in pressure, we have change in temperature, which we've explained in depth. We've gone into that one by one. We said change in concentration or partial pressures of the components is by adding or removing reactants or products. And then change in pressure, we say, is for gases, which depends on how a decrease in volume or increase in volume affects the pressure. And then change in temperature of the system. So those three stresses can only affect the equilibrium position of a reversible reaction. But take note of this. When an equilibrium system is altered, equilibrium will be re-established if you apply any one of these three stresses we have mentioned. Those three factors we have mentioned, those are the stresses. So when an equilibrium position, an equilibrium system is altered, so to try and annul it, to try and neutralize that effect, you must introduce any one of these three factors, these three stresses, not any one actually, any suitable one, to try and re-establish the equilibrium. And also note that among these three stresses, among these three factors, that is change in concentration, change in pressure, change in temperature, among those three factors, only temperature changes the equilibrium constant. Remember we said that only temperature changes the equilibrium constant. That's the K, since equilibrium constant has the symbol K. So only temperature will change the K value, the equilibrium constant value of a system. Other stresses, that's change in pressure, change in concentration, does not change the equilibrium constant, the K value of that system. That is, the equilibrium constant will remain unchanged. The equilibrium constant, I'm saying it again, will remain unchanged if there is change in pressure and if there is change in concentration. But if there is a change in temperature that needs to be done to try and re-establish an equilibrium, if it's a change in temperature, then it will affect the K value, the equilibrium constant value. So take note, only change in temperature affects the K value, the equilibrium constant value of a system. Okay, now let's see how to calculate equilibrium constants, calculation of equilibrium constants. So we see this question, because you remember we said something about this equilibrium constant stuff where we said that the active mass of a substance is the concentration, or the concentrations of that substance, but is raised to the power of its coefficients. So you need to remember this as you want to solve this question. Now, here's the question. Nitrogen reacts with chlorine to produce nitrogen trichloride at equilibrium. The concentrations of each gas were found to be N2 is 0.15 mole, Cl2 is 0.25 moles, and then NCl3 is 0.50 moles. So you've been given the concentrations of the of the different masses, the active masses. Now we are asked to calculate the equilibrium constant, Kc. So always remember, I'll say it again, that the active mass of a substance is the concentration of that substance that's been listed for us now, raised to the power of its coefficient. So how do you have these coefficients? Remember, before you have the mole number, those coefficients, you have to balance an equation. So here an equation was not given, but the sentence is given there. So we have to write the equation, the reaction, we write the equation of the reaction and then balance it. So if you see nitrogen reacts with chlorine, so of course you're going to have N2 plus Cl2 to yield what? Nitrogen trichloride. So it means NCl3 because trichloride, Cl3. So if we write out N2 plus Cl2 to yield NCl3, now let's balance the equation. Trying to balance that, you see that the equation will become 1N2 plus 3Cl2 to yield 2NCl3. I purposely call that 1, we shouldn't, but because we need that coefficient now to calculate. So we already know that if nothing is there, we also take that as 1. So, but I'm writing out that 1 because I want you to see how we use up that coefficient. So remember, the active masses are the concentrations raised to the power of their coefficients. Now we are given the concentrations in the equation, and now from balancing the equation, we've seen the coefficients of those reacting masses. So recall that the equilibrium constant is the ratio of the products divided by the reactants and raised to the power of their coefficients. That's the formula. If I didn't tell you that, then don't ignore recall. So know that now. The equilibrium constant, the formula for equilibrium constant is the ratio of the products divided by the ratio or divided by the reactants. So if you look at that, our balance equation, the only product we have there is NCl3. The reactants are N2 and Cl2. So we are going to divide the product by the reactants. But then as we are dividing that, we're going to raise those reactants and the products to the power of their coefficients, which are all written out there. So if we do that, then the equilibrium constant Kc will be NCl3, that's products. Remember, it's product all over reactants. We have only one product, so we put NCl3 products, and it should be raised to its coefficient. The coefficient is 2. That's the mole number there. Coefficient is 2, so we raise NCl3 to the power of 2. Then, since it's product divided by reactants, we divide it by the reactants. The reactant is N2 and Cl2. So we put N2, but we raise it to the power of its coefficient, which is 1. So we raise N2 to the power of 1, and then multiply by Cl2, and raise it to the power of 3. Now, that's just the formula. So we have NCl3 raised to power 2 divided by N2 raised to power 1 times Cl2 raised to power 3. That's just a deduction of the formula. So if we impute the masses, the concentration, of the products and the reactants, we see that NCl3 was 0.5 mole. So we replace NCl3 with 0.50 and still raise it to the power of 2 since NCl3 was raised to the power of 2. And then divided by we replace N2 with its concentration. N2 was 0.15, so we replace N2 with 0.15, and it still raised to the power of 1. And then we replace Cl2 with its concentration, which is 0.25, and then we raise it to the power of 3 since Cl2 was raised to the power of 3. Now, a quick one, if you put that in your calculator and solve it, you have your Kc value as 106.7. So, if you followed what I did, you can solve number 2 easily. Sulfur dioxide reacts with oxygen gas to produce sulfur trioxide. Almost the same thing as the other one. At equilibrium, the partial pressures of each gas were found to be 0.10 atmosphere, 0.30 atmosphere, and 0.45 atmosphere for SO2, O2, and SO3. That means SO2 has the concentration 0.1 as the pressure 0.1, O2 has the pressure 0.3, and then SO3 has the pressure 0.45 respectively. So we have to calculate the equilibrium constant, Kp. When we're to calculate the equilibrium constant of when we're dealing with concentration, we call it Kc. You know, equilibrium constant is K. The small c there was for the concentration. So now we are dealing with pressure, so we are calculating equilibrium constant, Kp. That's P for pressure. Now, if we write an equation and balance that, you have 2SO2 plus O2 in a reversible reaction yielding 2SO3. And if you look at that, product all over reactants, that's your Kp value, will be product all over reactants raised to the power of their coefficients. All spelled out there, you have SO3, that's the product, raised to the power of its coefficient 2, divided by SO2, that's one of the reactants, raised to the power of its coefficient 2, multiplied by O2, the other reactants, raised to the power of its coefficient, which is 1. And if you deduce that with the values of the pressures, you have 0.45 raised to power 2 divided by 0.1 raised to power 2 times 0.3. If you do your calculation well, you should have 0.2025 divided by 0.003, which will give you 67.5 as the equilibrium partial pressure constant. So we have a little tricky but simple question here to tackle. So listen carefully. Nitrogen monoxide reacts with oxygen gas to produce nitrogen dioxide. As shown in the reaction, 2NO plus O2 in a reversible reaction yields 2NO2, and the Kp value is given as 100. Now you are asked a series of questions. A, what is the value of the Kp if the reaction is divided by 2? B, what is the value of Kp if the reaction is multiplied by 2? C, what is the value of Kp if the reaction is reversed? And D, what is the value of Kp if the reversed equation is divided by 3? It's very simple to tackle, so we're just going to look at them one by one in a very short time now. So we tackle the first one first. What is the value of Kp if the reaction is divided by 2? Now, dividing the Kp value by 2 is like raising the power of the Kp value by half. You know that. So if we raise the Kp value by half, it means we are doing square root of Kp value. You understand? You divide if you square both sides. So Kp raised to power half is the same thing as square root of Kp. So that means dividing the Kp value by 2 is just like saying square root of the Kp. So square root of Kp is square root of 100. Square root of 100 is 10. So the value of Kp if the reaction is divided by 2 will be 10. You know the initial value of Kp in the equation was 100. But if the value of Kp is divided by 2, it becomes 10 because it is square root of Kp. That's Kp raised to power half. B, what is the value of Kp if the reaction is multiplied by 2? Now, multiplying a value by 2 is just the same as raising it to the power of 2, because it's just that times that to give you. So multiplying by 2 is like Kp raised to power 2, and Kp from the equation is 100. 100 raised to power 2 is 10,000. So if the value of Kp is multiplied by 2, or if the Kp is multiplied by 2, the value becomes 10,000. Now see, what is the value of Kp if the reaction is reversed? Now we have to write a reversed equation. You know, the forward equation was 2NO plus O2 to yield in a reversible reaction 2NO2. So if we have to reverse, the product shall have to will turn to the reactant side, so it will become 2NO2 in a reversible reaction yields 2NO plus O2. So that's our reversed equation. Now the new Kp value, since it's a reversed equation, will be sort of inverse of the Kp value. You're reversing, turning the product to the reactant side, but the same thing. So it's a reverse reaction, so it's an inverse of the Kp value. Inverse means 1 all over the Kp value. So the Kp value from the equation is 100. 1 all over 100 will be 0.01. So if the value of Kp is 0.01 if the reaction is reversed. And finally D, the value of Kp if the reverse reaction is divided by 3, so that reversed reaction 2NO2 to yield 2NO plus O2, let's divide all the coefficients by 3. So we'll have 2 all over 3 NO2 in a reversible reaction yielding 2 all over 3 NO plus 1 all over 3 O2, since O2 was just 1, so we divide it by 3 also. Now the new Kp value will be 1, since the reverse reaction is to still be in that 1 all over Kp, but the Kp now is raised to power 1 all over 3, since you are dividing the Kp value by 3. Yes, so dividing the equation by 3, so it will become 1 all over Kp raised to power 1 over 3. The Kp value is raised to power 1 over 3, so that means since the Kp value is 100, it becomes 1 all over 100 raised to power 1 over 3. If you solve that, you have 0.215. So if the reverse reaction is divided by 3, the new Kp value will be 0.215. Take note, there is no unit. Alright. Okay, let's see this last final question. Now, you know, these other questions we calculated, we're always given the concentrations. What if you come across a question where you're not given the concentration and you have to find them before you solve? That's this final question we're considering. 20 moles of NOCl is placed inside an empty 4-liter container. At equilibrium, 8 mole of Cl2 was found to be in the container. Calculate the value of Kc for this reaction. So first we write out an equation for that. So NOCl in a reversible reaction formed NO plus Cl2. So if you balance that, you have 2 NOCl gaseous to yield 2 NO plus Cl2. But first, we have to find the equilibrium concentrations for all the species there. Equilibrium concentration for NOCl, equilibrium concentration for NO, equilibrium concentration for Cl2. So in order to do that, we have to form an ICE table. ICE, ICE table. So ICE table, the I there means initial concentration, the C is the change in concentration, and then E is the equilibrium concentration. So we form the ICE table. This is how we do it. If we write out the balanced equation, 2NOCl in a reversible reaction yields 2NO plus Cl2, we'll discover that, and we write ICE vertically under the equation. I want to find the I value of the three species, the C and then the E. So now, for the I value, the initial concentration of 2NOCl, remember the question says 20 mole of NOCl is placed inside an empty 4-liter container. The 4-liter container is empty and only the reactant is placed inside there. So the products are not there yet. You understand? So the products are, the concentration of the products will be 0 because they are not formed, you know. So, but for the reactant NOCl, the concentration will be 20 moles divided by the 4 liters. So 20 divided by 4 is 5. So you have 5 moles of the initial concentration of NOCl. So you write 5 moles under NOCl. Getting to NO, which is the product, since the container is empty, NO and Cl, they have to be 0 concentration. They are the product. So the 4 liter container is empty, so you can't the products are not formed, nothing is there. Now so you write 5 moles under NOCl, write 0 under NO, write 0 under Cl2. Now that's I. For the C, that's change in concentration, we look at the equation, the equation there, the number of moles there. So the equation once more is 2NOCl yielding 2NO plus Cl, that's 1Cl2. Now, because the products are equal to 0, the concentration of the products are equal to 0, that means the reaction has to shift to the right, so as to favor the product. That side the concentration is less, so the reaction has to shift to the right, to that product side. Therefore, NO will increase by 2, since you see 2NO. It will increase by that coefficient there, by 2, and Cl2 will increase by 1, since the coefficient is just 1 there. So, but what will happen to the reactant side? The reaction is favoring the product side now because it has less concentration. So we'll be having the product side increasing while the reactant will be decreasing. So if the reactant is decreasing, then the reactants there too, the NOCl will be decreasing by that coefficient, not increasing as the product now. So the reactants will be decreasing by 2. So under change in concentration, we'll be having under 2NOCl minus 2x. Minus 2x because the reactant is decreasing since the reaction favored the forward direction. So minus 2x, but under NO you'll be having plus 2x, and then under Cl2 you'll be having plus 1x. That's for the C, the change in concentration values. Now the E values, equilibrium concentrations, you now have to, just like as if you're adding them up, you bring down everything. Under NOCl you have 5 moles, and then you have minus 2x. So you bring out that's 5 minus 2x, right? And then go to NO, you have 0 there, so you only have 2x, so you bring down 2x. You go to Cl2, you have 0 up there, so you only have 1x, so 1x is the same thing as x, so you just have x, you bring down x. Now the concentration of Cl2 at equilibrium is x, as you've seen. That's equilibrium concentration, the E is x. So, and we also know that from the equation, 8 moles of Cl2 is found to be in the container. 8 moles of Cl2 was found to be in the container. That means the concentration of Cl2 at equilibrium is 8 all over 4. 8 all over 4. 8 all over 4, just like we did concentration of NOCl. 8 all over 4. So if you do 8 all over 4, you have 2 moles. So we now have value of x as 2. Good. So value of x is 2. So if we have this value of x, then we can use that to find other species. How do we do that? Now, for NO, since we found x to be 2 moles, NO is will become, since it's 2x we had in the equilibrium concentration, 2x will become, where x is 2, 2x is 2 times 2, which is 4 moles. So we now find that x, for Cl2 we have 2 moles, for NO we have what? 4 moles. And then for NOCl is 5 minus 2x, where x is 2, we'll have 5 minus 2 times 2, that is 2 times 2 is 4, so 5 minus 4 is 1 mole. So we have 1 mole of NOCl producing the concentration, molar concentration now. The concentration of NOCl is 1 mole. The concentration of NO is 4 moles, and that of Cl2 is 2 moles. So we found the concentrations. Now we can use it to calculate our equilibrium constants for concentration for this question. So you have to go through that stages. And to calculate the equilibrium constant, it's not difficult since we already know that is the ratio of the product all over the reactants raised to the power of their coefficient. So you look at the equation one more, 2NOCl yields and 2NO plus Cl2. So we list out the product and divide it by the reactants. The product is NO and Cl2. So we write NO raised to the power of its coefficient, which is 2. So NO raised to the power 2 times the other product, Cl2 raised to the power of its coefficient, that's raised to power 1. You divide them by the reactants. The reactant is NOCl. We raise it to the power of its coefficient, which is 2. If we input the figures there, you have 4 raised to power 2 times 2 raised to power 1 all over 1 raised to power 2. Now if you multiply that, you have 16 times 2 raised to power, 16 times 2 divided by 1. 16 times 2 is 32. So if you divide 32 by 1, you have 32. So that's how to find equilibrium constant values of this equilibrium constant value when you're not given concentration. You have to first find the different concentration of the different species using an ice table. So you develop an ice table using this method, and at the end of the day you have your concentrations, and then you find your equilibrium constant value.